Am I audible?
Yes, sir. Good morning, sir.
Yeah, good one. So, how was your quiz yesterday?
Good, sir.
Good, sir.
Okay, the question was easy.
Yes, sir.
Okay, great. Okay, so today we'll start discussing on week 5, right? So, I mean, before the quiz, has anyone see the lectures of week 5?
The Kursi only first lecture.
Only first lecture, yeah. Okay. Okay, and what was about, what was in the first lecture?
It was about nullity.
Okay, great. So, can someone tell me what is nullity
Independent number of independent variables
of what?
of vector space or a matrix. Actually, a matrix basically of a homogeneous system rather.
But if I want the definition of nullity, what does nullity of a matrix mean?
The null space, that is the solution.
Exactly. Yeah. So let me start discussing from there itself. So in week 4, we have seen what was rank of a matrix, right? If we do the row reduction, then the number of non-zero rows after that, that is called the rank of a matrix, right? Now,
Right.
suppose we are starting with a matrix A, which is M cross N matrix. Okay. Now the null space of A is basically set of all vectors x such that Ax equal to 0. Now, where this x should belong? X is a vector. Now, what is the, in which space this x should belong?
It is the solution space of
Yeah.
That is
X.
okay, but what should be its dimension?
The dimension is the number of the
R1, no? It should be R.
No, not R. So, this is a M cross N matrix. So, x should come from
Yeah,
Rn,
N.
right?
Yeah, I
or
yeah.
yes, the
So,
number of
basically,
columns.
x, yeah, right. So suppose I have a matrix like this, say 2 cross 3. Okay. So I'm taking an arbitrary matrix. This is a 2 cross 3. Now this x should be 3 cross 1, right?
Right.
So x1, x2, x3. And this should be 2 cross 1.
2 cross 3. 2 cross 1, sorry.
2 cross 1, yeah.
Yeah.
So all these solutions for x will be our in our null space. Okay. So before going to solving this example, is this null space a vector space? Is subspace of Rn?
Yes,
Yes.
it is.
Why?
So because it is the solution space of Ax equals to 0. So if x and y is belonging to that null space, then the addition is also basically a solution to that equation, homogeneous equation. So it is closed under addition. And also scalar multiplication, we can also show it because it is
Yeah.
just a c is multiplied, and 0 is obviously a trivial solution to it.
Exactly. Correct. So 0 is obviously a solution because A0 is 0. So 0 belongs to null space. And as you have already pointed out, if x and y are in null space, that means Ax equal to 0 and Ay equal to 0. Then what about x plus y? And ax plus y is nothing but ax plus ay. Both of them are 0. So we will get 0. So x plus y is also in null space. This is null space of A. And similarly, for scalar multiplication, suppose x is in null space of A. That means ax equal to 0. Then A of some scalar multiple of x. It is nothing but C of ax. C of 0 and this will be 0. So Cx will be null space. So null space is indeed a subspace. Subspace of Rn. When A is M cross N matrix. Okay. So I am always taking A is an M cross N matrix. Okay. So if it is a subspace, then we can talk about it basis, right?
Yes, sir.
Hello, sir.
Yeah.
Actually, sir, I have joined right now. Means, can you tell what are the things that?
So we are basically discussing on week 5 topics. So we started with the first topic, which is nullity of a matrix. Right. So in week 4 we have learned about rank of a matrix. Now we are going to learn about nullity of a matrix or null space of a matrix. So null space means all those vectors such that Ax equal to 0. We have started with the matrix A, which is a M cross N matrix. Then all such vectors in Rn such that Ax equal to 0. Because if A is M cross N, then this X should come from N cross 1, right? So we can take it as a vector in Rn. And just now I have shown that null space is a subspace of Rn. Because 0 is there, it's closed under addition and closed under scalar multiplication. Right? Till now we have discussed till that much.
Okay, sir. Thank you.
Yeah. So as this is a vector subspace, then we can talk about the dimension of the vector subspace or basis of the vector null space. So, and the cardinality of basis is basically the dimension of null space. And the dimension of null space is nothing but the nullity of A. Is the nullity of A. Okay.
This is only applicable on homogeneous solution, right?
So this is the basically the solution space of homogeneous equation. System of homogeneous equation.
Okay, sir.
Okay. Yeah. Okay. So
Sir, I have a doubt, sir.
Yeah.
Sir, non-homogeneous solution cannot create subspace, right, sir?
no, 0 will not may not be there, right?
Yes.
Yeah. So let us take this example 2 0 1 1 2 1 and x1 this one what I have written and try to see how we can do that. So basically we are finding the solution space. So we already know what to use. We have to use Gauss elimination to find the solution, right? So this is our system of linear equation. Then what we can do? We can take this matrix and do the row reduction, correct? So what we can do for the first step?
R2 minus 2R1.
Okay, but at least first one we should.
Row 1 divided by 2.
So
na?
we have to
Divide the R1 by 2.
divide 2, yeah.
Divide by 2.
So we
But
can.
sir, we can, I mean, I'm just asking as a query, I can also do it afterwards. It's okay, na?
Yeah,
Okay.
any step
But-
is okay. But eventually the algorithm is basically start with a
algorithm is-
Okay, right.
Stepwise algorithm.
Yeah. So two things we can do here. We can do R1 by 2 here, or we can interchange R1 and R2. So I am interchanging R1 and R2. Then R2 minus 2R1. So what I get here is, this is 0, minus 4, minus 1. And then what I can do, R2 by 4 minus. So 1, 2, 1, 0, 1, 1 by 4. And another step, let me do it. So it is R1 minus 2R2. So 1, 0. So 1 minus half is half. 0, 1, 1 by 4. Right? This is the reduced lowest term form, right?
Yes, sir.
So which are independent variable and which are dependent variable?
X1, X2 are dependent, X3 is independent.
X1 and X2 are dependent and
Exactly.
X3 is independent.
So basically, if we multiply it with x1, x2, and x3, what I am getting, x1 plus half x3 is 0, and x2 plus 1 by 4 x3 is equal to 0. So x1 and x2 will be dependent on x3. So minus half x3, and x2 is minus 1 by 4 x3. Okay, so I can write my solution space as, so this is basically our null space. Okay, is basically minus half x3 minus 1 by 4 x3 x3. So instead of x3, I can take any t because it's a real number. So I want to avoid the variable, so I take x3 as t and then write it like this.
Sir, can you take the same example with the taking the scalar matrix kind of thing? Because they have mostly the independent variables. So how do we find in such a case actually the nullity?
Okay, yeah, great. So okay, let me finish this one, then I am coming to that. Okay.
Yes, sir.
Yeah. Why don't you prepare one example and tell me? Okay. Prepare one matrix and then tell me. Then I will solve that. Okay.
Yes, sir, any scalar, like you can take any.
Okay. Okay. So yeah. So first of all, what is the basis of this null space? Can you give me a basis?
Minus
So
1 by 2,
minus half.
minus 1 by 4 or 1.
Yeah.
So I can take t as 1. So minus half, minus 1 by 4, 1. So this forms a basis of this null space. And what is the continuity of this basis?
1.
1.
1, yeah.
Continuity is 1, no?
Cardinality is 1.
Dimension be 1 only.
So nullity of A is 1 here. Okay. So basically what we can see here, it is basically the number of independent variable, right? When we are solving this at the reduced low echelon form, at this step, the number of independent variable we can count, and that is basically the nullity of the matrix. Okay. So this is the number of independent variable.
So why is it happening, sir?
Yeah. Why is it happening? Okay.
Yes.
So what we are doing here, we are finding the solution of the system of linear equation, right? Because that is the definition of null space. Okay. Ax equal to 0. So basically it is the solution of the homogeneous system of equation where A is treated as coefficient matrix. Correct?
Okay, sir.
Till this step it is clear?
Yes, sir.
Now, when we are finding the solution space, so basically, suppose I am taking the solution space in Rn. Suppose the matrix is m cross n, then I am taking the solution space in Rn. And in
Sir,
Rn,
actually, in this case, I am saying that any value of x3 give me a solution for. Matlab, sir, if I am take any value for x3, then it will give, according to this equation, then it will give me a solution or a null space for this one.
Yeah. So exactly, if you take any value for x3, then x1 and x2 are fixed because x1 and x2 are dependent on that, right?
Okay. Okay.
So that is basically, if you take any value for x3 and write a vector, then it will generate, generate a subspace which will
Generate
be a
a
solution
subspace.
space for that. Okay.
Okay. Okay.
So it will be
Sir,
spanned by that. That's why. Yeah.
hello, sir. I'm sorry. Yeah, so actually, I'm just facing some lagging issue in my network. So I just want to know again the basis of null space, how to find using t. Like we can use in the place of t, we can use one some value we can place. So what are the values we can actually place to generate a basic basis of null space? Can we go with the zero also in that place for one of the some
No,
example?
so the process is, suppose we have two independent variable, right? So for
Yes, sir.
each independent variable, I can put one for T1, another for T2, right?
Yes, sir.
Now to find a basis, the general technique is put one for one independent variable. Suppose I have two free things, T1 and T2. So first put T1 as 1 and T2 as 0, then put T1 as 0 and T2 as 1. That will give you two different elements and that will generate the basis.
Okay, sir. Okay, sir. Got it, sir.
Yeah,
Yeah, it's the same like basis on the what we have learned
yeah,
earlier, right?
exactly.
In the
This is the same thing.
okay,
Yeah.
okay, yeah.
So this technique is not unique. Okay. So this is one way to find a basis. Okay. Even here in the same thing, I can take the basis as, suppose I am putting T as 4, then -1, sorry, -2, -1, 4. This is also form a basis, right? Basically, you can see this is a scalar multiple of this vector.
Yes.
Correct?
Yes,
So
sir.
this will also form a basis.
So
Okay.
this solution, what we are doing is just putting one independent variable to be 1 and another is 0. So can we use the same for the week 3 and week 4 to find the basis of any?
That is the method for finding the basis.
Okay.
Yeah.
Excuse me.
Yeah.
So actually, in this case, graphically, I am showing that in R3, a one line shows the null space for the whole
Exactly.
R3.
Exactly.
Yes.
Exactly. Yeah.
Okay.
Yeah, in
So we
R3, this is
always
a line because this is a one-dimensional vector subspace. And in R3, the one-dimensional vector subspaces are the line passing through origin. So this is one of those lines.
said that number of independent variable tells us the dimension of the basis. Hence, dimension is equal to rank. So I'm confused in rank nullity theorem.
No,
Why is
that's
it
what I
different?
have explained in the last revision session also. Rank of a matrix and rank of a vector space are two different things. Okay. So when we are talking about rank of a vector space, that means rank of a vector space, this is nothing but the dimension of a vector space. So sometimes we, instead of dimension, we can use rank. This is just a symbolism. Dimension of a vector space. Okay. And rank of a matrix means this is different thing. Rank of a matrix means, suppose I am starting with a matrix and
Number of
after row
rows
reduction,
echelon form.
after row reduction, non-zero in reduced row echelon form, the non-zero rows. The number of non-zero rows. So these two are different things, okay? Rank of a matrix means we start with a matrix, we do the row reduction, and at the end, the number of non-zero rows will give me the rank of a matrix. And dimension of a vector space is different thing. This is the cardinality of a basis.
That means these two have no relation in between them.
Directly, these two are not related, but eventually I will give you a relation between rank of a matrix and nullity of a matrix. That is the Rankine theorem. There is a relation. And yeah.
So just one query. I mean, if you are referring to the row space or column space of the matrix, then I guess the rank should be the same, right? If the vector space is the row space or the
when
column
we are
space
talking about some vector space and we're talking about the dimension, so for a vector space we can only talk about the dimension, okay? Otherwise dimension does not make any sense, right? Yeah.
Okay.
So in some of the questions, we often said that rank of a matrix or dimension of a vector space. So that's why
these two are different things.
So the value was same. in some of the questions.
When we are talking about vector space, then we can talk about the dimension of that vector space. Okay. So see, suppose I have this vector space. Vector space of 2 cross 2 diagonal matrix. Okay. Suppose this is V. Now, what is the dimension of V? Can you tell me how the vector space will look
Sorry,
like? I mean, how
diagonal
can we
matrix
write
two,
it
sir.
as a set?
Two.
Okay.
Is
Let her clarify her doubt.
Yes.
Yeah. So, can you tell me how it look like?
Yes, sir. 1001.
No, I mean in general.
A0 B. Yeah.
Right? This is where
Yes.
AB are in R.
R.
Correct?
Correct.
So all such matrix will be in vector space. Okay.
Yes.
Now, when I am talking about dimension of V, what I am talking, so we have to find a basis for it, right?
Yes.
So can you give me a basis of this?
A00 B.
A00B is a general form, right?
1001.
So first of all, this and this, right?
Yes, correct.
Two element will be there. So cardinality of this basis is 2. That means the dimension of V is 2. Correct?
Correct.
Now, in this vector space, there are many matrices, right? Infinite number of matrices, because AB can take any real number. Correct?
Yes.
So this one itself, suppose 2 0, I am starting with 2 0 0 0. This is a matrix in this vector space, right? This is a particular
Yes.
matrix in the vector space.
Yes.
Now I point it as A. Okay. If I say you, what is the rank of A? What will be its rank?
Rank will be number of dependent. Okay. One.
Number of non-zero rows, right?
Yes.
So currently it is not in row reduced echelon form because there is a 2. So what I have to do? R1 by 2, right? If I do R1 by 2, I will get this matrix. This is in row reduced echelon form, and the number of non-zero row is 1. So rank of this matrix is 1. Can you see the difference between dimension and rank now?
Yes, sir.
So
Also,
rank
we
of a
can say.
particular matrix, okay,
Yes, sir.
and dimension
So,
as the vector space.
Also, we can say the number of dependent variables denotes the rank of a matrix.
Number of dependent variable, yeah, in row reduced
Yes,
echelon
sir.
form. Yeah, correct.
Yes, sir. Okay, sir.
Okay.
Thank
So
you.
is the distinguish clear? I mean,
Yes,
why
sir.
these dimension and rank are different?
Clear, sir.
Sir,
Oh,
a slight
great.
Sir, I have one question.
Sir, if we are showing, sir, M cross 2 cross 2, sir, representation of matrix, sir, M 2 cross 2, in bracket, sir, it shows R. Sir, what it shows, sir, if it in bracket there is R square or R2, sir, and what it shows?
It can be. So each element is coming from R here. In those cases, each element is coming from R2 or R3, whatever that be.
Okay.
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 So what does closed under addition and closed under multiplication means?
If you take two elements from that space, the sum will be again there. Okay, that is closed under addition.
Okay.
And if you take one element from that set and take the scalar multiplication, then if it belongs to the set again, then it is called closed under scalar multiplication.
Okay, sir, got it.
Okay.
Sir, please scroll up. I want to take the screenshot.
Sir, I have one question. Can I ask?
Yeah.
Sir, just now you have solved one problem, and you found out basis for the given matrix, and at the end you mentioned that even in the videos also sir mentioned that that basis will span entire R3. I mean, if we have 3 elements, then it spans over R3, entire R3. Or
for which case? Spans. I mean, it does not necessarily always span R3. It depends on the dimension of the subspace, right?
Yeah, right. So means just now you solved one example, right, for nullity.
This one. So this one are you talking about, right?
Yeah, exactly. Same example I'm talking about. So, yeah, exactly. In this case, we got basis which is like -1/2, -1/4, and 1. So, can we say this basis will span entire R3?
Why? What is the dimension?
Dimension is 1.
1. So how can it span R2? What is the dimension of R2?
Dimension of R2 is 2.
2. So
because
at least 2 elements should be needed to span R2, right?
Sir, this is just a one point actually. So with one point, we cannot cover entire plane, right? So that's the way.
Okay, let him understand then.
Okay.
Yeah.
Yeah.
So to span R2, we need at least 2 elements, right? At least 2 vectors. There is only one vector, right?
Correct. Here
so
only one.
Can we span? I mean, can we expand whole R2 by this? No, right? I mean, what is the span of this set? What is the span of this set? Span of this set is this one.
Right, correct.
And this is not whole R2. Or this is, first of all, this is the subspace of R3 and this is a straight line.
Correct.
Okay, this is a subspace of R3. Okay?
Okay. So,
clear,
so if, clear. So, for example, if I want to say that this particular basis spans entire R3, that means the dimension must be 3.
There should be at least 3 vectors. Otherwise, how can it span?
At least 3 vectors. Okay.
At least 3 vectors. Yeah.
Okay. And follow-up question, like if we have 3 elements, I mean, if we have a basis, I mean, dimension is 3, then can I say it spans entire R3? Or again, I need to check some of the rules that whether it spans entire R3. No, for 3. I mean, for R3, dimension will be 3, right?
No. The dimension of R3 is 3. Yeah, right?
Yeah, that is what I'm saying. Yeah. So what I'm
I
saying
have not
is
got
that,
your question. What is your question?
Yeah. Okay. What I'm saying is that I have given one matrix, and then I found out that nullity, and then I found out basis, and I calculated dimension also. For that basis, dimension is 3, and even dimension is 3, and even the elements are like X, Y, Z form. I mean to say 3 points. I mean to say each element, each vector has X, Y, Z points. So in that case, can I say that the basis will span entire R3 as the dimension is 3?
Okay. So if I understand your question correctly, you have started with a matrix. Correct. You find the null space of it.
Correct. And then basis.
Then you find the basis of this null space.
Correct. I got 3 points. Null space.
Then in the basis, you have 3 vectors, V1, V2, V3.
Exactly, correct.
You are asking whether span of this set is R3 or not.
Yes,
right?
Exactly. Yes, exactly.
It is R3. It is R3. Because in R3, R3 means, first of all, we have to start with something cross 3 vector, right? If the null space is a subspace of R3, then it is true. Okay?
Correct.
You have to start with something.
Sorry
1 minute. Something M cross 3 matrix. Okay? Then you can talk about this as subspace of R3. Okay?
Correct. In the same thing, if I have like V1, V2, V3, and V4, then
first of all, you cannot get 4 independent vector in R3, right?
Okay.
How can you get 4 independent vector in R3?
Yeah, right. Now I'm clear.
Yeah.
Now it's clear. Thank you, sir.
Okay, great. Yeah.
So null space, like I'm still not very clear about it. Like, could you please?
Sir, I have a doubt. You just
1 minute, one by one. Yeah. Yeah, Amit, go ahead.
So that nullity part, I'm not like able to understand it.
Okay. So you have understood what is null space, what I have stated here?
Yes, sir.
Okay. So null space is basically, if you consider a matrix and take the homogeneous system of linear equation corresponding to that, and the solution space is basically the null space. Okay.
Okay, sir.
So we start with a matrix. So this is one example. We start with this matrix. We do the row reduction steps, and we eventually comes to the reduced low echelon form, right?
Yes, sir. Yes,
and
sir.
then there are some independent variable and dependent variable,
Yes,
and we have written down the solution space. So the solution space is the null space. Okay, and as you can see, there are two dependent variable
yes,
because
sir.
of these two pivot element and one free
One
variable.
independent, yes.
Yeah. Now the number of independent variable is basically your nullity. Why? Because this is your solution space. So I can take a basis of this null space because this is a vector subspace. So I have written down the basis, and the cardinality of basis is same as the number of independent variable, right?
Yes, sir.
Because we
Okay.
can put one there, right?
Yes, sir.
So here nullity is one. Okay.
Okay. Okay.
Yeah, that's what I have said here.
Okay.
Is
Got
it
it, sir.
clear?
Yes, sir. Thank you, sir.
Can I ask my question, sir?
Yeah, now you can ask.
Sir, my point is that in this question, that if A is a 3x3 matrix, okay, and it's a upper diagonal matrix, and the basis become 6, right, sir? That basis.
No, A is a particular matrix, right? How it have a basis?
No. For that is a diagonal matrix, sir. Upper diagonal.
So you are saying a vector space of diagonal matrices, diagonal 3x3 matrices.
The dimension is 6.
Only diagonal matrix or upper triangular matrix?
Upper triangular matrix.
Okay. So upper triangular 3x3 matrix. So dimension of A is 6, correct?
6, okay. So like 6 is a 6 dimension, okay. So is it representing, sir, R3, like which is a part of R?
No, why?
Why not, sir? Because it's a 3x3 matrix. Suppose it's coming from your if you each row column we consider as a X, Y, and Z plane. From a I mean talking of from a.
No, in representation they shows na ki every element belongs from which plane, R2 or R3.
1 minute, Hers. 1 minute. So this is a general form of this upper triangular matrix, right?
Yes.
And there are total 6 free places where I can put, so I can form a basis of that, and from there you can get the dimension of this vector space is 6.
Yes.
Okay. Now how R3 will look like? What is the general form of R3? I mean, how elements of R3 will look like? This is like this, right?
Yes, sir.
3 elements are there. So how this can be related?
No, sir, I'm just taking from a different point of view. Suppose there is a 3 homogeneous equation, x1, x2, whatever the coefficient, x1, x2, x1 plus x2 plus x3 equal to 0, whatever the A, B, C coefficient you can have. So from that point of view, if we can convert it to AX into B equation, we can get this form.
No, you are saying this is a vector space of matrices, right? When you are talking about Ax equal to something B or 0, suppose, okay, then this X will come from R3. That is different thing. You are taking a particular matrix from here. This is A, and this X is in the solution space of this. Okay, the solution space is the subspace of R3, not this matrix.
Okay. So that's means
got it, no?
Okay. That is itself a very.
So what you are doing, you are taking some particular matrix from here. Okay, A belongs to V. You are taking a matrix from this vector space. Now you try to find the solution space of A. Okay, and this solution space, this is coming from R3.
Okay.
Okay, because A is a 3x3 matrix. So whatever the solution space that should take like this. Otherwise, this multiplication will not be defined. Correct?
Okay, got it, sir.
So this is from R3, not this vector space. Okay. So till now, this is clear to everyone?
Yes, sir.
So nullity and dimension is same, no?
Nullity is basically dimension of the null space.
Okay, sir. Yeah.
Okay,
So
null
both are
space is
same.
a
It
vector
will find
space
the
and the
nullity and the
dimension of that
dimension.
vector space is the nullity. Okay.
Okay, sir. Yeah. Okay.
Okay, great. Yeah, someone has asked me about some scalar matrix. Yeah, who was that? Scalar null space of a scalar matrix. Yeah. No. Okay. So scalar matrix means it look like suppose 2. So this is all same and all this upper and lower are 0. So this is one scalar matrix, right? Can you tell me what is the nullity of A?
3. 0.
0.
0, sir.
So I got two answers, 3 and 0. Who is telling 3?
I think 0. Yeah.
0.
Because what I have to do again, I have to
Number of
find the solution
independent.
space like this, right? So I am doing the row operation here. So basically I have to divide all these row by 2. So this will give me an identity matrix. Okay. So the solution is x1 is 0, x2 is also 0, and x3 is also 0. So 0, 0, 0 is the
Is a dependent variable.
these are the dependent, everything is dependent variable, so no independent variable is there. So number of independent variable is your nullity. So there is no independent variable. That means nullity is 0, right? So this is your null space.
So that means for the scalar matrices, the trivial solution is the only solution that we can get.
Exactly, trivial solution is the only solution. Okay.
Sir,
And
I was
when
actually
scalar matrix, when these are non-zero. Okay.
Yes,
When
when
these are
yes.
Yeah.
So when
Yeah.
it becomes 0, then it is no longer a scalar matrix, right?
No, it is a scalar matrix. Zero matrix is a
Zero
scalar
matrix
matrix.
is a scalar matrix. Okay, okay.
Yeah.
Okay.
Yeah.
So the same thing applies for diagonal matrix also, right?
Same thing apply for diagonal matrix also. Yeah, correct.
But,
I mean, it
sir,
depends.
for
I mean, for
diagonal
diagonal
matrix,
matrix, this type of case happen, right? One element can be
yes,
0.
yes, sir, yes, sir. So it is
Oh,
So
the
you have
trivial
to
solution is
take the
not.
number of non-zero elements basically
Okay,
will give you
right.
the
So, but just a
sir,
small question in the diagonal matrix.
Sir, can you scroll up?
1 minute.
So, so in the diagonal matrix, the thing is short. So there the nullity can be like it can be at most 2, right, sir? Because if it is 3, it cannot be 3, right? Then it is no longer diagonal.
No, zero matrix is a diagonal matrix, no?
Okay.
All those can be 0. So zero matrix is a diagonal matrix, zero matrix is a scalar matrix. Okay. So for a non-zero diagonal matrix, it can be at most 2.
Okay.
Sir, sir, can you please repeat this? Why I think I have some network issue. Same example, because see, my doubt actually, sir. See what as we have learned from the last week. So if this is a matrix, okay, so because all the values are x1, x2, x3 are equal to 0, coming 0. So I'm just considering them as an independent variable, sir. Actually, so maybe I have some conceptual problems. So can you please explain this thing?
Till this part it is clear. This is the row
Yes, sir.
reduction
Yes,
form
sir.
of this one.
Correct, sir. Correct, sir. Correct,
Okay.
sir.
So how many dependent variables are there?
So for me, they all looks to be independent because they are not combination of any other vector, right?
No. The number of pivot element will give you the dependent variable. Dependent means either it is dependent on other free variables or it is constant. The constant is also, I mean, dependent.
Okay.
So here all the 3 are dependent variable.
Okay.
In the non-zero rows, if there is a pivot element, then that variable corresponding variable is your dependent variable. Okay. So x1 is dependent variable, x2 is dependent variable, and x3 is dependent variable.
All are dependent. Okay.
Yeah, there is no free variable here.
Because
okay. So no free variables means
I was confused with the previous, that knowledge, like Thanks, understood.
Now in previous also it was the case. I mean, it is the same thing. I mean, then you may have understood that incorrectly before. Okay, this was the case for previous also. Okay, this is the convention is same.
Maybe you are confusing it with rank, counting the number of rows with zero.
Maybe, but yeah. So now we'll make it clear. When if there is a pivot element in the non-zero row, then the variable corresponding to that is a dependent variable. Okay, dependent means either it may be a combination of the free variables or it is constant. What does it mean by free? Free means you can assign any number to that. But if the variable is constant,
variable,
then
yes,
can
any-
you assign any number to that? No, right? It is fixed.
No. Yes.
Correct? So it is dependent variable.
So the free that you are telling, it is the independent, right? Independent variable.
Yeah. Free and independent are same. Yeah. So this is clear, right?
Yes, sir.
So what is the dimension of this matrix?
There is nothing called dimension of a matrix. When you are talking about matrix, you can talk about rank of a matrix or nullity of a matrix. Dimension you can talk about when we are talking about some vector space.
Okay.
Okay. So here I have started with this matrix. I want to find the nullity of this matrix or rank of this matrix.
Okay.
So when I have found the nullity of the matrix, nullity has become 0. Okay.
Yes.
This is clear, right? And what is the rank of this matrix?
Rank is 3.
Rank is 3, exactly. So these two we can talk about this case. Okay.
If the question is find the dimension of this vector space, then what
Vector
would
space.
be?
So one matrix does not form a vector space, right?
Yes.
So what is your vector space? Then you have to mention which vector space are you talking about.
Okay.
So vector space suppose I am talking about scalar matrices, scalar 3x3 matrices. This will form a vector space, right?
Yes.
And then I can talk about the dimension of this.
Okay. And
So what is the dimension? So the
One.
matrix of this vector space will look like A0, 0, 0, A0, 0, 0, A.
Yes.
Right?
Yes.
So what is the dimension of this vector space?
1.
1, right? Because this will form a basis. This will form a basis, correct?
Yeah.
Last row 1.
Is it clear?
So 001 last row.
Is it clear?
No, sir. Can you please explain once more?
So general form of matrix in this vector space can be written like this. It is clear?
Yes. Yes.
This one till this one. Okay. Now, so this is the general form of the matrix. So this is my vector space, correct?
Yes.
Okay. Now my claim is I have to find a basis for this vector space. Okay. So
Yes.
there is only one free thing, A. Right? I am putting 1 over there. And I am claiming this is the basis of V. Why? So for basis means this has to be linearly independent and this has to span the whole vector space, correct?
Yes. Yes.
So is this set independent? This is a singleton set, right? So
Yes.
obviously this is linearly independent.
Yes.
Correct? And is it span the whole vector space? Yes, because if we take scalar multiple of this will give me the general form of this
Scalar
matrix,
matrix.
right?
Yes.
So this will span the whole space, right?
Mhm.
This spans V. So linear independent and span V means this form a basis. And the cardinality of this basis is, what is the cardinality of this set? 1,
3.
correct?
Oh, okay.
1.
Yes. Yes. No.
There
No.
are one element only. So
Yes.
dimension of V is 1. Is it clear?
Yes. Yes.
Okay, no?
Okay.
Yeah. Just take a look for some time, then it will be clear. Okay. Yeah. So, any other doubt till this point? Null space, dimension, rank.
No, sir. Clear, sir.
No, no?
So far clear.
Okay. Now, till now, what I have said, have you yourself, point out what is the relation between rank of a matrix and nullity of a matrix? Can you point that out?
So rank of A plus the nullity of the matrix A equals to the number of columns if A is a M cross N matrix.
Yes.
Why that is so?
Because when I'm taking each column as each of the columns there is a pivot element. The pivot elements are basically the rank. So the rest of that is basically the number of independent variables.
Yeah, correct. Yeah, you have got it correct. So suppose I have started with the M cross N matrix. Okay, this is my A matrix. There are some elements like this. What I am doing for both, for finding rank or finding nullity, I have to do the row operations, right? And eventually I will come to one reduced row echelon form. So this is my R. This is reduced row echelon form. In this place, when you have come, suppose there are some 0 rows. There may or may not be, but let's assume there are some 0 rows. And there are some non-zero rows, correct? Suppose till this one there are non-zero rows, and below that everything is 0. Okay. So the number of non-zero rows will give me rank, right? Non-zero rows will give me the rank of the matrix. Correct? Suppose there are L number of non-zero rows. Okay. Now, in these non-zero rows, there are pivot elements 1, 1, 1, like this. So how many dependent variables are there?
3.
1, 1, 1 is still L.
Okay. N minus 1. Like only wherever we have the one value, right? So that is dependent
So
on.
there are L, right?
Yes, sir.
L many dependent variables, right?
Yes, sir.
And how many independent variables are there?
N minus L.
N minus L.
Exactly. Because in these rows, there are no pivot element. The below, this N. Okay. This column. So till this point, there are this, and here there are no independent variable, N minus L. Okay. And this, the number of independent variable, this corresponding to the nullity, right? And rank is L. So rank plus nullity is L plus N minus L, that is N. So let me take a concrete example, okay? Then it will be more clear.
Sir, here I have a small doubt, like in that equation. So when you're talking about nullity, you just explained that we are talking about a vector space. And when you're talking about rank, it is also a vector space because it is the rank of column space or row space.
Exactly.
Okay, so both are vector space, like rank of A and nullity of A. Okay.
Yeah. Both are dimension of some vector space. Okay. Yeah. So in my previous example, let me go back there because we have already done one example. This one. So this is a 2 cross 3 matrix, right? After row reduction, I am coming to this step. 2 cross 3 matrix. This is my R. Okay. How many non-zero rows are there?
2.
2 non-zero rows. So rank of this matrix is 2, correct? So, and you can see there are 2 dependent variables, right? Because at those 2 places there are pivot element, right? for this column, there is no pivot element, right? So number of free variables or independent variable
1.
is 1. And that is your nullity. We have already seen that. And rank plus nullity is 3. This is your 3. Is it okay?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
So, sir, from here, the example, just scroll up once.
Huh.
So then, if I take this transpose, then nullity of A transpose is 0.
Nullity of A transpose.
Like from this, we can say because rank of A and A transpose is both 2 because it's same as column and row space. So then, since it is 2, then it will be 3 cross 2. The
Let's
transpose.
do that. Let's do that.
Okay. Yes.
Then it will be, we'll solve another example basically. So what was that? 201 201 121.
121.
So this is your transpose, right? Now
Yes,
I have, my matrix is 3 cross 2 matrix. Okay.
Yes.
What I have to do? I have to do the row operation. Correct?
Yes.
So
R1
let me take this as first, R1 and R3. I am interchanging this. Okay. Then R3 minus 2R1. So 0 minus 1. Okay. Then R2 by 2. Then this is 1 and this is 1. Correct?
Yes, sir.
So this is the reduced row echelon form. Till this thing, everything is clear, everyone?
Yes, sir.
Yes, sir.
Okay. Now this is till this step. There is number of, these are number of non-zero rows. So how many number of non-zero rows are there?
2.
2. So rank of this matrix is
2.
2. Okay. These are pivot element. So these are
Yes, sir.
dependent variable. And
Yes.
how many dependent variables are there?
2.
2. How many independent variables are there?
0.
0. There are no independent variable, correct?
Yes, sir.
Yes, sir.
Number of independent variables 0. Okay. And this is your nullity, right?
Yes, sir.
So rank is 2, nullity is 0, and 2 plus 0 is 2. Is it clear?
Yes, sir.
Yes, sir.
Okay, great. So this is another example where we can verify this Rankine theorem.
So is this the same example that we took above? Like it's the transpose of that?
It is the transpose of that. We
So
have
is it it is
taken.
affecting the nullity thing?
It will affect, no? Because
So then so while arranging the vectors in a matrix form, we can arrange it in column wise and row wise both, right? So in that case, it will affect the outcome for us.
Outcome for the nullity, yeah, right.
Okay.
Yeah, because nullity is particularly dependent on the how the matrix will look like. I mean, here you can see here this null space of this matrix. Suppose this is A. This is subspace of R2, right?
Yes, sir.
But in earlier case, it is a subspace of R3.
R3, yeah.
Okay, so they must differ, right? They are two different subspaces.
Okay.
Completely different subspaces, correct?
Yes, sir.
Okay. Okay, so till this is clear. let's come to this example, scalar matrix. Here what happened? Rank was 3, nullity was 0, right? We have calculated nullity to be 0. And as you can see, rank and plus nullity is basically, this is 3 cross 3. So this is your number of columns. Okay. So for some matrices, if you can calculate the rank, then you can already calculated, you have already calculated the nullity. And if you know the nullity of that matrix, you can easily say what is the rank of that matrix. Okay. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Great. So this was one of the important topic of week 5. Mostly the first 2 lectures was on that. So till this point, do you have any doubt? You can ask me.
So I have a doubt in one of the activity questions.
Sir, here I have some confusion. Sir, in the A transpose of the matrix that we just discussed of nullity, which have nullity of 0, it is a subspace of R3 or R2. This one,
R2, R2.
Sir, here
if you want to multiply something here, what should be the dimension? I mean, how this vector should look like? This is 2 cross 1, right?
Yes, sir.
Otherwise, it will not be defined. Correct?
Yes, sir.
So it is a subspace of R2. Okay.
Sir,
in earlier case, it was subspace of R3 because the matrix was 2 cross 3 matrix.
Subspace basically depend on the number of variables.
No. I mean, this is first of all, this null space is solution of this solution space of the x equal to 0. That part is clear, right? That was the definition.
Yes, sir.
Now, when I am writing ax equal to 0, this x, where this x belongs, that will depend on the number of columns of A, right?
Yes, sir.
If A is a m cross n matrix, then x must be from Rn.
Rn.
Right?
Yes,
so
sir.
when I am talking about 2 cross 3 matrix, then this x must be from R3. When I am talking about 3 cross 2 matrix, then x must be from R2. Is it clear?
Okay, sir. Thank you.
Okay, great.
Sir, I have it.
Yeah.
Activity question 5.2.
So someone before you
Sir,
also have
yeah.
some
Yes, sir.
activity question. Yeah, let me do that first, then I'll... Yeah, which one?
Sir, 5.2. 10. Level 2 first question. Level 2 first question. 10.
This one,
Yes,
right?
Yes, sir.
Okay, Ax equal to 0 be a homogeneous system of linear equation which has infinitely many solutions, where A is a m cross n matrix. Which of the following are possible? Yeah, I mean, now we should do that, right?
Yes, sir. So if it's a if it has independently infinitely many solutions, then so there are independent variables. So the last one is obviously true because nullity is not equals to 0. Because there always exists some independent variables or free variables.
Right.
And the first one is that m is less than n. That means the number of rows is less than the number of columns. So rank of A can be why it is equal to m? Like it can be at most equal to m, right, sir?
No. I mean, which of the following statement are possible? Rank of A is m and
okay, so
m
yeah,
is
it
less
is
than
possible.
n.
So it is possible, but it is not okay. But sir, the last nullity of A equals to n. That's I'm not understanding why it is possible.
I mean, this case is possible, right?
So can
this
I
is
just
equation where A is m cross n matrix, which of the following is possible? Okay. First of all, nullity of A is n. That is an interesting thing. Okay, so let me do this. So suppose I have 2 cross 2 matrix. This is a 2 cross 2 matrix, right? 2 cross 2 0 matrix.
Yes, sir. Yes, sir.
Correct. What is the nullity of this?
It is
2. Nullity of this 2. What is the null space of this? Can you tell me?
R2.
Null space is any x1, x2.
Exactly. Is whole space
Whole
R2,
R2. Yes.
right?
Yes. Yes.
You take any vector that will give you 0. Correct?
Yes. Yes, sir.
You can write any vector that will give you 0. Any, right? So this has infinitely many solutions, right?
Okay. Okay. Okay, sir.
So this
Okay.
case is
Got
also
it.
possible.
Okay. Got it. Got it.
Correct?
Yes.
Great.
Okay. So it is basically referring to the zero vector.
Ah,
When
exactly.
okay. Okay.
Yeah.
A zero matrix. Sorry.
Yeah. Okay.
Sir,
Okay.
sir,
Thank you, sir.
what is the
So
difference?
first of all, let me point here one other thing. So suppose in this 2 cross 2 matrix, A is 2 cross 2 matrix, right? Okay, let me write it in fresh page.
Excuse me, sir.
Yeah.
Sir, what is the difference between variable and vectors?
I mean, there is no similarity between variable and vector. Okay, I will come to that. I have to know what you are asking me first of all.
What is variable, sir? Okay.
I'm coming to that. Okay, let me clarify this first. Okay, suppose I have some n cross n matrix. Okay, and it is given that nullity of this is n. What can we say about A?
It's a zero
It's an
matrix.
identity matrix, so scalar matrix.
Not
Nullity is
identity
A.
matrix.
So it is a zero matrix.
Zero
A
matrix.
must be zero matrix, right?
Zero matrix. Yes.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Why?
You just showed to me like in previous.
No, I showed the opposite of that.
Okay.
I showed that if it is zero matrix, then it is n. But now I am telling the converse is also true. The
So then the
nullity of a matrix
rank
is
of the matrix is 0. Rank of matrix
rank
is
of the
0.
matrix is 0.
Then the column should be the entire nullity. If rank is 0, then your rank plus your nullity equal to your number of columns. Okay.
That is n. That is okay.
So,
but why the matrix should be 0?
So then there is no non-zero row, na?
Yes, sir.
Non-zero row after row reduction.
Yes, sir.
But I am saying from the beginning it is a zero matrix. Why?
So both columns are independent.
I mean there are n number of columns.
So that is the only possibility where we get the rank of A equals 0.
So suppose A has some non-zero row. Okay.
There won't be any pivot row, sir. That is
exactly. Yeah. Suppose there is one non-zero row. Okay. Then after row reduction, at this column will be non-zero because there will be a pivot, right? At the first place. Or at least some element where there will be pivot, right? If there is some non-zero row. So at least if there is some non-zero row, then after row reduction, there should be at least one non-zero row. Because one singleton vector is always linearly independent, correct? Is it clear? But in this case, this is not happening. Okay, rank is 0. That means from the beginning itself, all the rows are 0. Okay? Because in earlier some activity question, there was a question like this. Suppose A is a non-zero matrix, then rank must be greater than 1.
Yes, sir. It was there.
Greater than equal to 1.
Yes, sir.
Because at least the first row should be independent. Any one row. Okay, any one row should be independent if it is a non-zero matrix. Right?
Yes, sir.
But in this case, that is not happening. Rank is 0 means all the rows must be 0 from the beginning. Okay?
Right, sir.
Okay.
So with that we can conclude that if rank of A equals 0, that means that A must be zero matrix.
A must be zero matrix. Exactly.
Okay.
Exactly. Yeah. Someone was asking about variable and vector. Who was that?
Sir, I'm asking.
So what do you understand? What do you mean by variable?
Sir, variable is something for which values vary. Like x
Right.
is dependent on y, so these are variables.
Suppose I have this x1 plus, sorry, x1 say minus 2x3 equal to 0. Then x1 equal to 2x3. I can write it, right?
Mm.
So these are variable, right? I can take any value for x3, and whenever I am fixing x3, our x1 will get fixed, right? But both of these x1 and x3 are variable, correct?
Mm-hmm.
Because for depending on the value on x3, x1 will be changed, and for x3 I can take any value, right? So both of these are variable. Now what is
Okay.
vector? What is a
Vector
vector?
is vector is which gives directions also. I mean,
But in mathematical language, what we have learned from with 3 and 4. So suppose I have vector space, okay, and all the elements of that vector space are basically, we denote it as a vector, right? Suppose in R3, I am taking 1, 4, 0. This is a vector in R3, correct? Because R3 has a vector space structure with addition and scalar multiplication, correct?
Yeah, yes,
So
yes,
any
correct.
element of R3, we can call it a vector. Okay. So is the distinguish clear? I mean, basically there is
Yes,
no
sir.
relation between these two.
Okay, yeah, sure. Okay, sir. Thank you.
Okay, great. Yeah, someone was asking about some other activity question.
Yes, sir. Week
Yeah,
5.2, question number 6.
5.2, question number 6.
Yes, sir.
Which of the following options are correct for a square matrix of order n cross n in natural number? If the determinant is non-zero, then the nullity must be 0. The nullity must be non-zero. Okay. Okay. I mean, now you can tell me that. So what does determinant non-zero means?
It must be in
Later.
Yeah, sorry,
Answer
sir.
that, okay? Yeah, go ahead. What does determinant non-zero means?
the vector must be independent, sir.
There should be some independent vector, right? I mean,
Yes.
all the vectors are independent, basically.
Independent.
All the rows or all the columns must be independent. So suppose all the rows are independent for n cross n matrix. Then what is rank? Suppose I have a n cross n matrix. Okay,
All
n
independent,
cross n
sir.
matrix. Okay, let her answer that because she asked that question. Okay, and determinant A is non-zero. Then you have said all the rows are linearly independent. Correct?
Yes, sir.
Now, what is the rank of A then?
0.
No, n.
N.
All the rows are independent, no?
N,
So
sir.
after row reduction, all the rows will be non-zero.
Yes, sir.
Okay? So rank of A is n. Now, so what is the nullity then?
0.
0. Is it clear? Because rank plus nullity should be equal to n.
Yes, sir. Yes.
Correct? Yeah.
Yes.
So if determinant is non-zero, then nullity must be 0. Correct?
Okay. Okay, sir.
Got it,
Okay.
no?
Yes, yes. Thank
So
you, sir.
now you can answer this. I will not tell you for option 3 and 4. Okay? Now you just figure it out.
Yes, yes. Yes, sir.
Okay? Okay, great. Yeah. Any other doubt till this point? This week 5 is basically not so difficult because first two lectures are on nullity, then there is only linear mapping and linear transformation.
Yes, sir. Actually, a linear mapping and transformation
I will come
concept
to
are
that.
not.
I will
Yeah.
come to that. Linear
Till
mapping.
here, I'm good. Yeah, till here, whatever you have explained, I'm clear.
So let me just ask once to everyone. Is there any doubt till this null space and nullity?
No, sir.
I think you can attempt the questions now, so you'll get that. Okay.
Yes, sir.
Great. Yeah, here there is a question: nullity of a zero matrix of order n cross n. So, what is this true?
Yes, sir.
Yes, sir.
Yeah. Okay. Great. The rank of n cross n matrix of all whose entries are equal to 1. What will be the answer?
N.
N, sir.
No,
All entries are 1.
One. Oh, all entries are
One.
Because remaining rows will become 0.
Exactly. Because suppose start with the 2 cross 2. Okay. This is a 2 cross 2 where all entries are 1. After row reduction, what you will get? This will become 0, right? So at least 1 should be non-zero. Okay. So rank will be 1. Correct? And this is true for all n cross n matrix. Okay. So this is also clear. And these I have already mentioned. This you have to find by doing row reduction. Ax equal to 0 be a homogeneous system of linear equation which has a unique solution. Okay, then what is the nullity of A?
0.
Because unique solution means 0 must be a solution anyway, right? So there cannot be any other solution. Correct?
Yes, sir.
So 0 is the only solution and that is in the null space. So the nullity is 0. Correct?
Yes, sir.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
great.
Yeah.
Great. Okay.
So this question.
Suppose 14.
Yeah, go on, sir. Sorry.
Yeah. So suppose x1 non-zero solves Ax equal to 0 where A is 2 cross 4 matrix. Okay. 2 cross 4 means 2 rows and 4 columns. So what is the minimum number of elements in a linear independent subset of null space of A that also spans the solution space of Ax equal to 0? Okay. So how should we approach this?
So it's a 2 cross 4 matrix. So the maximum rank can be 2.
Maximum rank can be 2, exactly.
Yes. So it is basically if it is the addition is basically equals to 4. So the minimum can be a 2 only.
And what does this first one means?
Which one?
I mean, x1 not equal to 0. What does this statement mean?
It means the trivial solution is not being counted.
There is at least one non-trivial solution.
Right? One non-trivial solution.
So null space is non-zero. Okay. Null space is non-zero and rank can be at most 2. Right?
Rank
at most 2. So the null space must be more than 2. Okay.
That means we can say that solutions could be infinitely number of solutions.
Yeah, correct. Okay, so yeah, I think you can try this.
Sir, 15th question. 15th question, sir. Here.
15th question, you just have to find the basis which can form a basis.
Just approach. We will
so
here, go on, sir.
No, ask your doubt.
Sir, here we have to represent them in matrix form and then row reduce, right?
Exactly. Or you can find the determinant. That is also possible. So suppose, first of all, S1, S2 and S3, these are from R3, right?
Correct.
And these are 3 vectors. So 3 vectors is R3 can form a basis if they are linearly independent.
Correct.
Right?
Yeah.
If they are linear independent, then I know that it must span R3. Okay. So write this as a matrix form. I mean, as a column of a matrix. Then calculate the determinant. If the determinant is non-zero, then they are linearly independent. In that case, it must form a basis. That is for S1, S2, and S3. Now for S4 is coming from R2. there are two vectors. So again, this can form a basis if this is linearly independent. So you write the matrix, you calculate the determinant. If the determinant is non-zero, then these are linearly independent, then it forms a basis. Correct?
And yeah, and S5 is not basis.
S5 cannot form a basis because there are three vectors, and in R3, maximum number of linear independent vector can be 2. Correct? So this cannot be linearly independent. So this cannot form a basis.
Yeah.
Clear?
Thank you, sir. This one you explained earlier, so we could connect it. Yeah. Thank you.
Okay.
Sir, how S5 cannot be a basis?
Because there are three vector in R2, right? But in R2, the maximum number of independent variable can be 2. Is this clear?
Yeah. Okay.
Because dimension is 2. So more than 2 vector cannot be linearly independent.
Yeah, got it.
So there are 3 vectors, so they cannot be linearly independent, and as they cannot be linearly independent, they cannot form a basis because basis must be linearly independent. Okay?
Yes, sir.
Okay. Now let's go to the next section, which is linear mapping and linear transformation. Okay. So linear mapping means what? Suppose I am taking in this side Rn and this side Rm. Okay. So Rn means x1 to xn, right? This is A. And this side basically take some combination of this x1 to xn. So let me write it explicitly, then it will be more clear. A1 x1, A11 x1. Taking linear combination of this. So there should be m variable, I mean m coordinate.
So every element should consist of all the elements from Rn.
I mean they can be 0, but at least that is a combination of x1 to xn, right? Linear combination. So this is, as we are taking linear combination, that is why it is called linear mapping. And there is another aspect, another perspective that I will come. Okay. So basically, this type of mapping is called linear mapping. Okay. So basically, I am taking, if I take some vector from Rn, then the linear combination of the coordinates of that vector will give me the image of that vector. Okay. If such a map exists, then that map is called linear mapping.
Sir, actually, we are converting the matrix in the system of linear equations.
Exactly. There is a relation between this mapping and matrix. Okay. So till now we have only talked about matrices. Now there is a relation between mapping and, I mean, why this matrix is really important, that will come in the picture. Okay. So that is in week 6, basically. So matrix corresponding to linear transformation. So that we will discuss later. But this portion is clear, right? What is linear mapping, at least?
Yes, sir.
So what this vector denotes, basically, what is this vector? So suppose I am writing like this. I have written down in form of a matrix. If I multiply this with this vector, then what I get? Then I get these elements, right? The first one is this A11 x1, A12 x2, A1 and xn, correct? Similarly, A21 x1 dot A2 and xn. am1 x1 amn xn. Correct? So basically there is some matrix A. If I multiply with a vector from Rn, this Ax is in Rm. Correct? So I am taking a vector in Xn. The mapping will give me Ax for some matrix A. This type of mapping is called linear mapping. Okay, and linear mapping can be expressed via a matrix. Okay, is it clear?
Yes, sir.
Yes, sir.
Okay. Now suppose Rn, the same thing. So here it is x. So here it is x means it is x1 to xn. This is explicit. Okay, and then it is ax for some matrix A, and A is from m cross n R. Okay, A is some matrix of m cross n R, and this Ax is inside Rn. Now in Rn there is a vector space structure, right? So first of all, where does 0 go? 0 vector A into 0 for some matrix A, and that is always 0, right? So 0 vector must go to 0. Okay, if I take two vector x and y in Rn, so x goes to where? Ax, y goes to some ay. Now where does x plus y goes?
A times x plus y.
Correct? So basically your fx is ax, if y is ay, then f of x plus y is ax plus ay. That means fx plus fy. Okay, and what about c scalar multiplication cx? A of cx, that is c of ax. That means f of cx is c of ax, that is c of fx. So this is one thing, and this is another which we got, and that is basically give us the idea what is linear transformation. So in general, I can write it V to W. V and W are two vector spaces. T is a linear transformation. Okay, when we call it a linear transformation, this is a map between two vector spaces. So vector spaces means it comes with a addition and scalar multiplication on both the sides, and this linear transformation will respect that addition and scalar multiplication. What does it mean by respect? That means if we take two vectors v1 and v2, it will respect the addition of those two vectors, and T of CV is basically C of TV. This is for all V belongs to V, and this is for all V1, V2 belongs to V. Okay, so 0 will always go to 0. If we have these two, we don't really have to mention that, because if we take C to be 0, then you can see that T of 0 must be 0, right? Clear, no?
So take an example.
So I will take an example, but at least this part is clear, right? How from linear mapping we can came to the conclusion about in general linear transformation. Okay, so let's see.
Sir, what is W? W is a vector space.
Both of those are vector space. Okay, W must be a vector space. Otherwise, in this side, how can we define this addition and this scalar multiplication?
Yes, sir.
Yeah. So suppose R2 to R3.
But here, no elements are from W, right? Here for 1 and 2 conditions, so we are not using any elements from W.
This TV1 and TV2 are in W, right? So this addition is in W. This addition.
Oh, okay. The output will be in W.
Output will be in W. This is a mapping, no?
Okay.
So it is the domain, it is the codomain.
Okay.
Okay, you remember the mapping in maths 1, right? In maths 1 we have done this.
Yeah. Somehow.
So yeah, the left side is domain and the right side is codomain. Yeah. So suppose R2 to R3. Okay, I am defining P of x comma y. Any element of R2 is from x comma y, right? Okay. So is this a linear transformation? What we can check? We have to check these two elements, right? First of all, 0 is going to 0, right? Whenever you see something, you just check first that whether 0 is going to 0 or not. Okay. What is t0 comma 0? This is for just first 0 check.
0.
All zeros.
All 0, right? So this is 0, 0, 0. So this is 0 comma 0 comma 0. Yeah. So any 0th check is satisfied. So in some cases you will see that this will not go to 0, then immediately you can say this is not a linear transformation. That's why this should be checked first. Okay. Then take two element, right? Take v1 to be x1 comma y1, v2 x2 comma y2. What is v1 plus v2? x1 plus x2, y1 plus y2. So what is t v1 plus v2? T of x1 plus x2, y1 plus y2. Now, what is this? So the mapping is 3. Now x is your x1 plus x2, y is your y1 plus y2, comma 2 of y1 plus y2, comma 3 x1 plus x2 minus 2 y1 plus y2. Okay, so this is 3x1, 3x2, 4y1, 4y2, 2y1, 2y2, 3x1 plus 3x2 minus 2y1, 2y2. This is the image. And this we can write it as 3x1 plus 4y1, 2y1, 3x1 minus 2y1 plus 3x2 plus 4y2, 2y2, 3x2 minus 2y2. Is this portion clear? Because if you add these two, the addition is coordinate-wise addition, usual addition.
Yes, sir.
This will give me the first one, this is second one, this is the third one, right?
Yes,
So
sir.
the first element is t of x1 comma y1. This is t of x2 comma y2. That means
satisfies
t of b1 plus t of b2. Similarly, you can do it for scalar multiplication, right? The same approach. C take cv1, so cx1 comma cx2, and then c will come out from this side. Okay, I am not doing it. Okay, so this is a linear transformation, right?
Yes, sir.
So in these cases, when you are trying to find whether something is linear transformation or not, so all the time you don't have to check all this. First of all, check whether 0 is going to 0, and then just see that whether this is a linear combination of x and y or not. Some power is there or not. If there is some power, then it will not be a linear transformation. Power of x and y. Okay, all the x and y should be of degree 1. And
Sir?
it should be a linear combination. Then only you can say that this is a linear transformation.
Sir?
Yeah.
Sir, tell me if I am wrong, sir. Actually, sir, we are in the linear transformation from R2 to R3. We are actually taking a coefficient matrix of A 3 cross 2 and multiplying it by a 2 cross 1 matrix. And then we are getting a 3 cross 1 matrix that is from R3.
Exactly.
Okay.
So that is what I have written here. This one.
Okay, sir.
Correct?
Okay, sir.
Yeah. So check whether that is some linear combination of your x and y or not. I mean the coordinate of the vectors on the left side or not. Okay. If that's happens, then it is a linear transformation. So
then if we are doing an addition or a scalar multiplication on left side, it respect right hand
It
side.
respects the
Respect
addition.
the.
Yeah, exactly,
Okay,
exactly,
okay, sir. Okay.
exactly. So let me see whether there should be some question like this.
5.5 question number 2.
Yeah. So let me see. So first one, R2 to R3.
Sir,
Whether
before that, please repeat the last statement. Sir,
so
how the
basically,
matrix?
So basically, what you have to check, you have to check whether 0 is going to 0 or not, and then you have to check whether these. So there are two coordinates, right, in R2, x and y.
No, sir, matrix. How the matrix
Okay, this
form?
one.
Yes.
So
How
here we have
he
a vector
converted
form.
this?
Sir, theory part is complete for week 5.
Yeah, theory part is complete for week 5.
Okay, sir. Thank you, sir. Great session.
Yeah. So this portion, we have a vectors in. So these are linear combination of these coordinates, right? Can you see that?
Yes, sir.
Each coordinate is a linear combination of the coordinates of Rn, correct? Some linear combination. Then I can write this vector as a matrix into these vectors in Rn. So if I take this matrix, so take the first coefficient of x1, second coefficient of x2, and the nth coefficient of xn and write it as a row. Multiply with this, I will get the first coordinate. Similarly, a21, this is a21. Then there is a22, this is your a22, and then a2n. I have written this here. Take the multiplication with x1 to xn, I will get the second coordinate. Is it clear?
Yes, sir.
So suppose in this example you want to see.
Yes.
So this is how we can write this matrix. So this is 3, 4, 0, 2, 3, minus 2. If you multiply with x, y, what is the first coordinate? 3x plus
3x
4y.
plus 4y.
This is 3x plus 4y. What is the second coordinate?
2y.
2y. This is 2y. What is the third coordinate?
Yes. 3x minus 2y.
3x minus 2y. You got it, no?
Thank you, sir. Yes, sir.
Okay. So yeah. So for the second problem, so is 0 is going to 0? No, right? Because 0 is going to 0, 0, 1. So this is not a linear transformation. Okay. For the second one, is 0 going to 0?
Yes.
Yes, sir.
Now you have to ask whether it is a linear transformation or not. So is it a linear transformation?
Yes.
Yes, sir.
No. The first element is x, y. So the degree is 1 plus 1. That is 2.
Yes, sorry.
Right? So basically where it will fail, so txy is xy into x plus y. This xy is not a linear combination of x and y, right?
Yes, sir.
This is some product. So basically, if we take, suppose I am taking c into xy, okay? So this is tcx Now what is tcx This is cx into cx plus cy, correct? So c square xy, c x plus y. If I take c outside, still I have a c inside there, and this is x plus y. Okay?
Yes, sir.
And what is t of cxy? This is cxy x plus y. These two are not equal, as you can see. Right?
Yes, sir.
So this will fail. Because this element xy, this is not a linear combination of x and y. Okay?
Yes, sir.
Clear, no? So this is not a linear transformation.
It will, I mean, it will pass in that addition rule, but only.
No, addition is also not going to pass.
Okay, I will check that.
You can check the addition will also not going to pass.
Okay.
So actually, we cannot find the matrix, right? Because
exactly.
Yes.
Because it is not a linear transform. I mean, linear combination. That's why we cannot find the matrix. Okay. Yeah. Then third one, is it a linear transformation?
No.
No.
No, sir.
Because 0 is
No,
not
sir.
going to 0, right?
Yes.
Yes.
Fourth one?
Fourth one, yes.
Yes,
Fourth
sir.
one, yes, because 0 is going to 0 and it is indeed a linear combination of x and y. Okay. Fifth one?
It is also a linear combination.
Fourth one is also linear, exactly.
Yes, sir.
Last one?
No.
No, sir.
Again, there is x into y, so it will again fail. Okay. Okay. Okay.
I have a
Now,
related question.
Sir, I was small.
I have a related question. Please tell me if I am correct. If a linear map follows all the rules of, the three rules, basically the zero rule, the addition rule, as well as the scalar multiplication rule, then it is a linear transform.
I mean, linear mapping itself is a linear transformation, but we use linear transformation only in case of vector spaces. It is more general. Linear mapping is only from some Rn to Rm. Okay, only for Rn, but there can be different type of vector spaces, right? As you can see that set of matrices is a vector space, right? In that case also we can talk about some mapping, and that is called linear transformation. Okay.
So
Linear mapping we only can talk about from Rn to Rm.
So generally it goes to lower dimension to higher one. Just R3 to
No,
R2.
that does not necessary. So here is an example from R3 to R2. Question number 4. Okay. R3 to R2. Linear transformation defined as Txyz to x plus y and y plus z. Right. This is a linear transformation. Correct?
Okay.
Which is going from higher dimension to lower dimension. It can happen. Then which one the following statement is true? So first one is
true.
0, 0, 0 is going to 0, 0. Yes, it is
Yes.
correct. You just have to check whether these are satisfied or not. Then the last question is whether it is injective or not. So do you remember what is injective and surjective for a mapping?
One-to-one mapping.
Yes,
One-to-one
when yes, sir. For if x
One
equals to
input, we are
f of
going
y,
to
then
get
x equals to y.
one output.
Exactly. So V1 equal to V2 implies V1 equal to
V1
V2.
equals to V2.
So this is injectivity. Okay. Now from here, in case of vector space, I mean in case of linear transformation, we can do it slightly better. So my claim is let me write it this way. T is injective linear transformation if and only if, this is if and only if T v equal to 0 implies v equal to 0. Okay, what does it mean? So we always know that T0 is 0, right?
Yes, sir.
T of 0 is 0, that we always know. But 0 is the only vector which is going to 0. If that happens, then T is injective. Okay, this statement is saying that.
Sir, can you repeat, sir? Last sentence.
So I am saying that T of 0 is always 0, right? This is always true. This is always true. This is from the definition itself. Now, this statement is saying, what this statement is saying? This statement is saying that if 0 is the only vector which is going to 0. So this is your V, this is your W. So 0, there is 0, 0 is going to 0. So here is 0 of W, right? This is 0 of V. So this is always true. Correct. Now, in general, other vectors can also go to 0. No issue there. There can be some cases where other vectors can also go to 0. But for an injective linear transformation, only 0 vector is going to 0. There is no such other vector which is going to 0.
So it's like infinitely many solution for the other case, right?
Kind of like that. Not kind of, eventually that is the same thing. When we will talk about the matrix representation of linear transformation, then you will see that that is the same thing. But even before going there, before going to the matrix, we can directly say it from here. How? So let me take an example. First of all, that other vector can also go to 0.
So one question, like what about other elements like non-zero elements?
So I will come finish that. Then you can, if you have
Can you
still you have
scroll
doubt,
up a
then you
little
can
more?
tell me. Okay.
Can you scroll up a little more, sir?
Okay, sir.
So first of all, let me give you one example where other element can also go to 0 if it is not injective. Suppose T of xy is going to x minus y and say what? 0. Okay. Let me write this. Okay. So this is a linear transformation, right?
Yes, sir.
This is a linear transformation, right?
Yes, sir. Yes.
Yes, sir.
T of 0, 0 is going to 0, 0, correct?
Yes, sir.
Yes.
Can you give me any other vector which is going to 0?
Y, y.
One comma one.
Whenever x and
One
y
comma
are
one.
equal, then it is going to 0.
Yes.
Right?
Yes, sir.
So if I take 1, 1, this is also going to 0.
Yeah.
Right? So what I am getting? So I am getting 0, 0 and t of 1, 1. These are same, but these two vectors are not same. So t is not injective. Correct?
Yes, sir.
Yes, sir.
So I am seeing one example where two different vectors are going to be 0, and that so clearly that is not injective. But this statement saying the converse is also true. That means if t is injective, then there does not exist two vectors which are going to 0. Okay. So let me prove this statement. Okay. This example is clear, right?
Yes, sir.
Yes,
Yes.
sir.
Okay. So first of all, t is injective. This is given. I will show that to show what I have to show. TV equal to 0 implies V must be 0. Correct? This is the first thing we have to show. Okay. So TV equal to 0. I want to show that V must be 0. So this is quite straightforward. T of 0 is also 0. T of V is T of 0. As T is injective, then V must be 0. So this question is clear, right?
Yes. Yes.
Correct?
Yes, sir.
Okay. Yeah. Given t is in. Okay. Yes, sir.
Now the problem comes when we want to show the converse. Now given TV equal to 0 implies V must be 0. To show T is injective. So T is injective means suppose there are two vectors V1 and V2 such that T V1 equal to V2. I want to show V1 and V2 are equal, right? I will take this on one side. So this is 0. V1 minus V2, this is 0. Now V1 minus V2 is a vector which is going to 0. What is given? Whenever TV is 0, then V must be 0. That implies V1 minus V2 must be 0. That implies V1 equal to V2. So T is injective. Is it clear?
Yes, sir.
Yes, sir.
Okay. So for checking injectivity, it is enough to check whether there is any other vector, non-zero vector, which is 0 going to 0 or not. If there is any other non-zero vector which is going to 0, then T cannot be injective. Okay.
Can you explain with some example?
I have started with that example. No? So this mapping, is this injective?
Yes, sir. Yes, sir. Got it.
This is not injective, right? Because there are one non-zero vector which I have written down here, which is going to 0. Right? As soon as I find some vector, non-zero vector, which is going to 0, then it cannot be injective. Okay, if it has to be injective, then only 0 has to go to 0. There should not exist any other vector. Okay.
Okay,
Yes.
sir.
So basic if you understand as a functional perspective, so one input must produce only a unique output, right? That's mean
that is the basic definition of injectivity in case of function.
Correct. So say like
But for
same
linear
here.
transformation, we can say little bit more because there is a concept of zero.
Okay.
Right? So for linear transformation, what we can say more? That if there is some non-zero vector which is going to zero, then T cannot be injective.
Yeah, correct.
Okay. Yeah. So that is an advantage for linear transformation.
So just what about the surjective part?
I'll come to that. First of all, let me ask you whether this is question number 4, whether T is injective or not.
No, Pranal, it's not injective.
Why?
Because if I take xyz 1, -1 and 1, it will also go to 0. And
Exactly.
0 vector.
Exactly. Correct. Very good. So then in that case, T is not injective because we can find a non-zero vector which is going to 0. Correct?
Yes.
Very good. Yeah. Now, yeah. So this is the statement which I have just now I have proved, right? T is 1-to-1 linear transformation if and only if there does not exist V not equal to 0 such that T will equal to 0. Right? This statement I just now have proved. Correct?
Yes, sir. Yes, sir.
Yes, sir. Yes.
Okay. And okay, now let's come to subjectivity. What do you mean by subjectivity?
So the
In case of
codomain
function.
equals to range.
Many possible.
Not domain equal to range. Domain equals range.
Codomain equals to range.
Codomain equals range. Yeah. So what does that mean?
Sir, over here, if like
every
V is
in
W,
codomain
then
should have
So
element.
every
of
output
V,
element will be there in the range actually.
Exactly. For each W in W, there exists V in V such that
TV is equals to
TV
W.
equal to W. Okay. Okay. So this is the definition. Then T is subjective. This is the basic definition. Okay. Okay. So let me go a little bit further. We know what we will define what is kernel of T. Kernel of T means all those vectors in V such that TV equal to 0. Okay. This is called kernel of T or null space of T.
Sir, can you repeat again, sir? This is new for me.
Sir, both are same, sir. Null space and kernel.
Null space of T and kernel of T are same. That is basically set of all vectors in V which are going to 0. Okay.
So why is it called kernel, sir? If it's the same.
Why is it called kernel? I mean, there is no reason for calling it kernel. So null space or kernel are basically the same thing. Kernel means set of all vectors which are going to 0. That is by definition. I mean, there is no particular reason why it is called kernel. Okay. So this is the null space of T or kernel of T. Okay. The definition is clear, everyone?
Yes, sir.
Sir, take example, sir.
So just a small doubt. Like in the previous example, you showed that it is when it is injective, there must be a single V.
There must be some non-zero vector which is going to 0. Yeah.
No, if it is injective, I am saying, then there is only 0 which is going to 0.
So in this case, kernel must be 0.
Kernel must be 0. Okay.
Yeah.
Sir.
So that is the point. If T is injective, then kernel of T must be 0. That means only 0 vector. Okay. Okay. So let me take an example. So the previous example which I have taken, let me do that. Okay. So this is my linear transformation T from R2 to R2. Okay. So what is the kernel of this? So kernel means set of all vectors which are going to 0. That means, so let me write it, kernel of T or null space of T, all xy in R2 such that T of xy is 0, 0. So So xy in R2 such that T of xy means what? X minus y comma 0. It is 0 comma 0. So x comma y in R2 such that x equal to, so x minus y equal to 0. That means x equal to y. So basically x comma x, so x in R. So all these type of vectors are in kernel, right? Is
Yes,
this
sir.
clear?
Correct, sir.
Yes,
Correct,
sir.
sir.
Okay. Now let me state another fact here. So this kernel or null space of T or kernel of T, these are same thing, is a vector subspace. Vector subspace of phi.
Sir, can you scroll up a little? Yeah, just a moment.
I will upload this in folder, no issue. Okay. I will upload this PDF. Yeah. So why this is a vector subspace? So first of all, this is your V. Let me draw this diagram first. This is your W. Here is something called 0 of W. So basically kernel means all these vectors which are going to 0. Okay. This is the kernel. This is inside V, right? This is T. Correct? This picture is clear?
Yes,
Yes,
sir.
sir.
Okay. Now I am claiming this kernel is basically a subspace because first of all, T of 0 is going to 0, right? That is 0 belongs to kernel of T. Correct? Because 0 is always going to 0. Secondly, if V and V1 and V2 are in kernel of T, what does it mean?
So can we say it is many to one?
V1 plus V2 is also belonging to kernel.
So they're
So
making
T of
0?
V1 equal to 0. Yeah.
T of V2 equals to 0.
T of V2 equal to 0. So T of V1 plus V2,
Is
that
equals to
is
T of V1 plus V2 is equals to 0.
0 plus 0, that means 0. So basically V1 plus V2 is also in the kernel.
It is also like a many to one kind of system situation, right? This is
I
also,
mean, whenever it is not injective, then it is many to one. If it is injective, then it is not many to one. Correct?
so this is surjective, right?
No. I mean, I have not gone to subjective yet. Why this is subjective? Subjective means it has to be doing something with image.
Okay, yeah,
I
right.
have not come to image it now, till now. Okay. Then if V is in kernel of T, then TV is 0. Then what about T of CV? This is C of TV and this is 0. Correct? So CV is also in the kernel of T. So kernel of T is a vector subspace. Is it clear?
Yes, sir.
Okay. So till this portion it is clear. So kernel
Yes,
is a vector subspace. Okay.
Sir, is this week 6 content?
Yeah, it's week 6. It is the first lecture of week 6, but I just want to mention it before that. Okay. Okay. So till this portion it is clear, right? I will not go further deep now, but at least this portion is clear, right?
Yes, sir.
Yes, sir. Yes,
Kernel
sir.
of T is a vector subspace, and the point was whenever T is injective, kernel of T is the 0 subspace. Okay, and this is if and only statement. Both sides is true. That we have already shown. Correct? And for image, what we have said, if image of T is W, Image means T of V, right? Set of all for all V belongs to V. This is your image of T. If image of T is the whole space W, then T is surjective. Correct?
Yes, sir.
Okay. So now you can check whether a space is surjective or not. You can always do that, right?
Yes, sir.
Okay. So suppose this example 6. And example 6 means T is R2 to R2. The linear transformation T of xy equal to x comma 0. Whether it is on to or not. This is the question. So let me write this. First of all, is T injective?
No, sir.
Why?
No. 1, 0, 2,
Many like
there are
1,
many
comma
non-zero
0,
vectors
2,
which is
comma
going to
0.
0. So the answer is no. Because T of 1, 0 is also going to 0, 0. Sorry, not 1, 0.
0, 1.
0,
0,
1.
1.
Yeah. I mean,
So now is T surjective? Is there all vectors in R3 which have a pre-image?
No, sir.
No, no.
No, sir.
Can you give me a vector which has no pre-image?
2, 3.
Whenever there are some non-zero element at Y, then it has no pre-image. So 0, 1, let me take, it is in R2, in codomain, okay, has no pre-image, correct?
Yes, sir.
And last,
Sir, can you explain this image and pre-image concept?
that was in maths 1, right? You should explain to me. What is pre-image?
Sir, particular vector.
No, forget about vector, just in terms of mapping, in terms of function, what is pre-image? Suppose A to B, there is a function f, okay? So I am taking B belongs to B, some small b. What is the pre-image of B?
A small a belonging to A.
If there exists some A belongs to A, such that fa equal to B, then this A is called pre-image of B, correct? Now, if every element of B has the pre-image, then we call F to be surjective, correct? That was the definition.
Yes, sir. Got it, sir.
Got it, no? Yeah.
Yes, sir.
So here I am taking 0, 1 is in R2, but it does not have any pre-image because there is no x, y such that it is going to 0, 1 because x, y is always going to x, 0. So the second coordinate must be 0, but here second coordinate is 1. So it does not have a pre-image. Clear?
Yes, sir.
Okay, great. And lastly, if T is both injective and surjective, then T must be, then T is an isomorphism. I mean, whenever T is bijective, we call it isomorphism.
So, sir, like in this example, T of xy is equals to x comma 0. So, if can I generalize and say that if the span is not R2, then it is not surjective.
Span of what?
X comma 0.
Span of x comma 0. X comma 0 is not a particular vector, right?
Like if it is a vector space, then the
but
span
x
of
comma
that.
0 is not any particular vector, right? I mean, here x can take any real number. You can say span of 1 comma 0.
Yes, span of 1 comma 0. Yes.
Yeah, basically here image, what I have said at image, this image is also a vector subspace, correct? You can check it.
Yes. Okay.
Why?
Sir, so here span of 1
Sir,
comma 0 is the image, sir.
So image of T image is also a vector space. You are discussing that,
Why?
right?
First of all, is 0 there?
It's
Yes,
a 0,
because
0 vector is there, sir.
because it is in
No,
W.
forget about this in general.
Sir, not all the cases, sir. Suppose it's a x comma 0. If there's a x comma 1 is there, it may not be a vector subspace, sir.
Then it may not be. Then in that case, it is not a linear transformation, right?
Yes.
X comma 1, that is not a linear transformation, right?
Yes,
So
that
I
is
am
also.
saying when T is a linear transformation, then image must be a vector subspace. Can you check that? Okay. So let me.
Yes, so span of 1, 0 will be the image, sir, right?
Exactly right. So it is not R2, then it is not surjective. Yeah, you are right. But before that, you have to identify that image of T must be a vector subspace. This is in general I am talking about, okay? Not any particular example. So first of all, image of T means I have written TV such that V belongs to V. This is the image, definition of image. Now 0 belongs to image of T, right? As T of 0 is basically 0. Then suppose two element I have taken V1 and TV2. These two are in image of T. Then what about sum of these two? This is T of V1 plus V2. Now V1 belongs to V and V2 belongs to V. Then their sum must be belongs to V. So this is one image of V1 plus V2. Right?
Yes, sir.
This is the image
Yeah.
of V1 plus V2. So this is in the image, this sum. And what about scalar multiplication? Same thing, right?
Yeah.
T of
Yes, sir.
V is in the image. Then
T of C,
C of
C
TV.
into T of TV must be in the.
This is T of CV, and CV
for all
is
CV belonging to V.
V. So this C of TV is in the image of T. So
Yes,
image
sir.
of T is a vector subspace. Okay. Okay. So in this case, our image is basically this vector subspace, right? This is vector subspace, basis of image of T. So we can take one basis. This is 1, 0. This forms a basis, correct?
Yes, sir.
Because this 1, 0 will span the image, right?
Yes, so
and this image is subspace of R2. This is not whole R2.
It's a proper
That's
subspace.
why it is not. That's why it is not surjective. Proper subspace. Clear?
Yes, sir.
Okay.
So in the first example that you solved, that is R2 to R3. Can you scroll up once?
No, I have taken R2 to R2.
Sir, first one, the first problem.
This one.
Yeah, this one. Sir. So what about this? Like, here, can we do the same way, like in this finding the span?
First of all, tell me what is the, I mean, whether it is injective or not.
Okay. So T of 0 is going to 0, but I have to find another vector which is going to.
Which is going to 0?
So no, because the second is 2y. If I it can only become 0 when y is 0. So no positive value of y can go to 0. That I can surely say. But whatever x and y.
So let me write it here.
So then 3x plus 4y must be equals to 0, and the last part must be equals to 0, and x not equals to 0.
The first one was 3x minus 3x plus 4y. 2y, 3x minus 2y, 3x plus 4y. This, right? This was the transformation.
Yes, sir.
Suppose this is going, some vector is going to 0. That means what? This
3x
is
plus
0.
4y equals to 0. Yes.
This is
2y
0.
equals to 0.
This is 0. Is there any vector other than x, other than 0, 0 is going to 0? That is our question. So basically what we have to do, we have to find the solution of this set.
तुम्हारी क्लास के बीच में से डिस्टर्ब करा है तुमने ठेका ले रखा है मुझे परेशान करने का
Can you please switch off your audio?
मेरे ईयरफोन नहीं है मेरे को एक ईयरफोन है ना उनके
Somebody is-
मेरे ईयरफोन ले
Sir, I have a doubt. So for injectivity, we can.
So we can solve this system like in the form of a matrix.
Yeah, right. Right.
Just, sir, if we solve this,
So it will even this will also give the only x, y, 0 only, sir. Like only that is the solution.
Okay, 1 minute. Yes, Shashi, something you are saying.
Sir, if this matrix, when we get trivial solution to be the only possible solution, then it's injective.
So that's what you have to check exactly. That's what it is. Whether this system has a unique solution or not. If it has a unique solution, then this is
injective transformation.
Yeah. So let me write this for 0, 2, 3 minus 2. Okay. What I can do here, this is R1 by 3. Okay. 1, 4 by 3, 0, 2, 3 minus 2. Then what I can do here, R3 minus 3 R1.
3 R1.
1, 4 by 2, 4 by 3, sorry, 4 by 3, 0, 2, this is 0, minus 2, minus 4, right? So minus 6. Okay. And then what is there?
R2 by 2.
R2 by 2. So 1, 4 by 3, 0, 1, 0 minus 6. Then
R3 plus 6 R2.
Exactly. So 1, 4 by 3, 0, 1, 0, 0. So this is enough, but still if we want to do this 0, then we will do R1 minus 4 by 3.
4 by 3 R2.
So 1, 0, 0, 1, 0, 0. So the solution is x1 equal to 0 and x equal to 0 and y equal to 0. Right? So this is the only solution.
Yes.
So this is injective. Exactly.
Okay.
Okay. Clear now?
Yes, sir.
Okay, great. Subjectivity you do yourself now. Okay.
So here you have not taken the augmented matrix, right? Just the left hand side part.
Because here Ax equal to 0. For Ax equal to 0, we don't have to bother about the augmentation. Right? Because if we take the augmented matrix, here always be 0, 0, 0.
Yes, sir. Yes, sir.
So we don't really have to bother about that. So clear, no? Now you can see why, everything is related from what you have learned from first week. Right? The solution system,
So that means
solution of system of linear equation that will come every place wherever you go.
So till week 8, so all the concepts will be interrelated, right?
Even after that also. Okay.
For injective solutions, if it's to be an injective, that there's only solution should be a trivial solution. That's it.
Yeah, exactly.
Sir, if it has no solution, then we can say that it is surjective.
Can Ax equal to 0 have no solution?
Yes.
No, it always
has a solution. Because 0 is always a solution.
Yeah, that is true.
So
but if we have to check that it is surjective or injective, that is where we find it here now for injectivity.
For subjectivity, what do you have to do?
There should be no image of some image, then it is surjective. Then there is a way that we can check that how it is surjective or not. Yeah.
For subjectivity,
infinite solutions for Ax equal to 0, right? So
No. For injectivity, you are taking Ax equal to 0 and you will check whether the solution is unique or not.
Determinant
If
of
the
this
solution
matrix is
okay, 1 minute.
non-zero, then we can say that it has unique solution and it is injective. Like that, there is any way that we can say that it is surjective or not?
Exactly. So this is from R2 to R3. Okay. So in this case, what you have to do, you have to take any vector from here, right? Any vector B. So B is of the form. So in general, you are taking, so suppose A, B, C. This is the vector from R3. Now if you want to find a P-image for this, what you have to do? Whether the P-image exists or not means, this is the system of equation you are getting, right?
Yes.
In general for ABC. Now try to find whether this system has a solution or not. In this case, you have to deal with augmented matrix.
And for that, if it has no solution, then we can say that it is surjective, no?
If it has a solution, then it is surjective. If it has no solution, then it is not surjective. No solution means what? There does not exist any xy for which this is your image.
So that's means,
right?
sir, x, y, and z. Like suppose x, y, and z. So x should be the solution would be x value plus a one independent value, x plus v, and y also should be y value.
See, actually, I did not want to say this in week 5 itself, but actually, whenever you check injectivity, you really don't have to bother about subjectivity because there is something called rank nullity theorem. Rank of T plus nullity of T equal to dimension of V. Okay, it is in week 6 although. So we have already know that kernel and image both are vector subspaces, right?
Yes, sir.
Okay, so dimension of kernel is your nullity that I have already mentioned somewhere. Nullity of T, and dimension of image is rank of T. Okay, and T is from V to W. Okay, so and there the theorem states that rank of T plus nullity of T is dimension of V. Okay. Now in this case, T R2 to R3, the example which we are dealing with, what is nullity of T then? What is nullity of T?
It is 2.
0.
It is 0. It is 0.
It is injective, right?
Only trivial.
Injective means nullity must be 0, right? Because kernel is the 0 subspace.
Yes.
So nullity is 0, correct? So what is rank of T?
3, sir.
2.
2. Dimension of V was 2.
Yes.
Right? So rank is 2. What is the dimension of codomain?
3.
3.
Okay. Dimension of codomain of T is 3. This is the dimension of image, right? Rank means dimension of the image. It is less than dimension of the codomain.
Oh, okay, so you cannot. Yeah. So it is not surjective.
So there's another concept like some functions are isomorphic. So can you explain one example where it's isomorphic?
So isomorphic means what? Isomorphic means
both,
it is both
one,
surjective
one
and
and
injective, right? So suppose T, okay, T R2 to R2 I am taking. This. Okay, now tell me, what is the nullity of T? First of all, what is the kernel of T? Kernel is easier to find, right?
We have a lot of possible solutions.
Kernel is 0.
Really?
Sorry, no sir, trivial solution.
It is 0.
Only trivial solution, right?
Yes.
Okay. So kernel is basically 0 vector, right? So nullity is 0. Kernel is 0 vector, nullity is 0, so T is injective. Okay. Now come to that. Now rank of T plus nullity of T is dimension of V. nullity is 0 here, right? So rank of T and dimension of V is same. What is dimension of V?
2.
2. So rank is 2. Correct?
Yes.
And image is a rank means dimension of image set, right?
So it is surjective.
Now image is inside the codomain, right?
Yes.
That is bijective, no?
This is T. This is your domain. This is your codomain.
Can you explain once again this last part?
I am explaining this. Okay. So this is your domain. This is your codomain. So 0 is going to 0. I have seen that. Image is inside the codomain, and the dimension of the image and this dimension of the codomain are same. So image and codomain are basically same here. Image of T is basically R2 here because both of them have same dimension. So what I have done here, first I have found the kernel of T, which is easy to find by solving system of homogeneous equation, homogeneous linear equation. In that case, I am getting nullity of T is 0. That means T is injective. Now I want to know whether T is surjective or not. By using Rankine theorem, I can find it easily. So Rankine theorem says nullity is 0, then rank must be equal to dimension of V. Now dimension of V is 2 because V is R2 here. Okay. So rank of T is 2. Now dimension of rank is basically dimension of image, so that is 2, and it has the same dimension of W, the codomain, right? So image of T and R2 are codomain, basically the same. So T must be surjective. T is surjective.
Sir, if the rank and dimension are equal, so that's the only case where we'll get the image to be both isomorphic, right? So,
if the rank and dimension, if the rank and dimension of the codomain are same, then it is surjective.
Like equivalent to bijection.
Is it clear?
Yes,
If rank means dimension of the image. Okay.
So, sir,
if rank and dimension of the codomain are same, then it is surjective.
So, sir, if any R2, if you go to R2 to R3, it cannot be surjective, right, sir?
No, it can be.
No, it cannot be. Exactly. But Rankine theorem shows that. Okay. First, let me clarify this portion. Okay. So in this case, T is injective and T is surjective. That means T is
bijective.
That means T is isomorphism. This is clear, right?
So
now you say what more Rankine theorem is saying us. T is from V to W. So if T is injective, then nullity is 0. Then rank must be dimension of V. Rank and the dimension of V must be same, right? Now suppose I have a mapping from say R3 to R2. Okay. My question is, can T be injective? Can T be injective?
No.
Why?
Like all the elements will not have a single element. Like
no,
it
from
can
Rankine theorem you can say it directly, right? Just know what I have said.
Yes, sir.
So there are three
if T is
equations and
injective,
two
then nullity
variables.
is 0. Yeah.
So I will always get independence. So nullity can never be 0.
So suppose T is injective. Okay. Suppose T is injective, then nullity is 0, right? Then
Yes.
what about rank? Rank of T must be dimension of V
3.
must be 3. But
Yes.
can rank be 3? It
No,
cannot be, right? Because it must be inside codomain.
Right.
Dimension of codomain is 2. So rank cannot be bigger than 2. Right? Because rank of T must be less than equal to dimension of the codomain. Correct?
Yes.
So this type of mapping from R3 to R2 or basically Rm to Rn where M is greater than N, then T cannot be injective. Okay? Is it clear
Rm to Rn, yes, M is greater than N. Yes, sir.
So can you write that statement?
If M is greater than N, then T can't be injective. It is clear to everyone? Because if T is injective, then the rank of this should be M, right? But M is greater than N. The dimension of the image cannot be greater than the dimension of the codomain, right? Because it should be inside codomain. So must be dimension should be either equal or less than that. Clear?
Yes, sir. So
Is it clear to
here we
everyone?
can, yes, sir. So here you can say that there are n, there will be n equations and m variables.
Right.
So and n, so number of equations is less. So
You can relate it in that way also.
yeah, okay,
Same
okay.
thing.
Yes, sir. Yes, sir, understood.
Yeah. So this is one more thing, and we can know. So and eventually, what it is said that if T is isomorphism, then dimension of V and dimension of W must be equal.
For this condition check, we'll first check for injectivity and then we'll check for rank and dimension.
Yeah. So rank of T plus, it is easier to check basically. This is dimension of V. Now T is isomorphism means what? It is both injective and surjective, right? So injective means IT is 0. Injective means nullity of T is 0. That means rank is same as dimension of V. And T is surjective means what? T is surjective means rank of T is same as dimension of W.
Yes.
So this dimension of W and dimension of V is same. Clear?
Yes, sir.
Yes, sir.
Okay. So yeah, even we covered some topics from week 6 also.
So in the last one, you showed that R3 to R2, that if now the opposite, if R2 to R3 is there, then yes, sir. Yes, sir. So then the nullity, what can you say about the injective part?
You tell me, what can you say?
Okay, so
We have to take some function, right? So can we say
Here
directly?
I mean, directly we cannot say anything about this, right? I mean,
yes,
here it can be
you
injective.
have to take a...
Yeah, it depends on the function. Without seeing the function, we cannot say here. Because nullity can be 0 also, 1 also, anything can happen, right? Because we have some space for the codimension.
Yeah, okay, sir.
The rank can be 2. Yeah. I mean, in this case, it can happen like this. Nullity can be 1 and even rank can be 1. This case can occur, right? So in this case, it is neither injective nor surjective.
Yes.
Yes. This case can happen, right? 1 plus 1 equal to 2.
Right.
So this can happen. Even this also can happen, right? Nullity of T is 0. So it can be injective and rank T can be 2. This can happen, right? But you can say
that
one
it is
thing,
not
like
surjective.
rank T cannot be 3.
Yeah, so we can say that it is never surjective.
It is never surjective. Yeah, you can say that. But for injectivity, we cannot say anything.
It can be or
it
may
can
not
be injective, cannot be injective. It depends on the function.
Yes. Okay.
Okay. But surjectivity can never be surjective.
Okay.
Okay.
Yeah.
Okay. So whatever we have done today is clear, right?
Yes, sir. It was a great session. It was a great session.
A great session, sir. Thank you.
Learned a lot of things.
Okay. So hopefully this, because linear transformation is really important. If it's clear from the beginning, then I think we will get through the...
So will you upload this?
Yeah, I will upload this.
Okay.
Because
Sir, where will be able to find this this PDF?
There is this portion.
Supplementary section.
Supplementary under supplementary.
Supplementary. There is live session summary, right?
Okay, sir. Okay, sir. Thank you.
Yeah, here if you go, then you have a download option.
All the previous notes also available over there.
All the means I have uploaded everything, but
Yes,
not.
you have uploaded. Yeah, yes, your lectures are already there.
Yeah, many sessions are uploaded here. Yeah, I mean those which we think are important is uploaded there. Okay. So,
so for till week 8, there will be a continuation from linear transformation, sir.
Till week 8, no? Yeah, till week 8, there is linear transform. But even after this week 9, 10, and 11, these are also related to this, what we are doing here. Okay, so these are also related to that. So, have any of one see you any question of previous term?
No, sir, I have not seen.
You see the question in every previous term we have given one question which is relating all the weeks, all the 11 weeks.
Okay.
There is one comprehension question, comprehension type, which relates all the concepts of every week. So for you there will be a question like this also.
Yesterday also there was one question which was like comprehensive of all 4 weeks.
All 4 weeks, yeah. We generally try to give such a question because that will show you that whatever you are learning are somehow related. Each week are related, and you will need
But
that
those carry
actually
like
the
a
things
lot
from
of
other subjects are also very related to Max 2, sir. So
yeah, definitely.
But
I mean, if you go to machine learning foundation, then you will start from here, the rank and nullity of a matrix.
Okay, sir.
Because there we have to find eigenvalues and eigenvector, and you have to talk about eigenspaces.
Sir, I have a doubt, sir. For last term, previous term, we had weeks separately for eigenvectors, eigenvalues, right? So this time we don't have.
No. We don't have it in Math 2. No, we don't have it in Math 2. It is in MLF, Machine Learning Foundation. Okay.
So this vectors and everything will be continued in MLF course also. Means same.
Right.
Okay.
Right. I mean, these are all the basis of the MLF course.
Okay, sir.
Okay.
But thank you, sir. Today's session was really great. I mean,
so
we learned
it was a great session. Thank you
yes,
so
sir,
much.
it was very helpful today. Yeah.
Okay. Thank you. Bye.
Yeah. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you so much, sir.